Okay, I booted into Windows just because it works very well with projectors, so glad this is working. All right, so we've already done introductions. I work at NVIDIA within the Performance Lab. The Performance Lab is responsible for all internal and external performance data. So in particular, I work on the NGC product we'll talk about to deploy HPC and HPC visualization containers. And before joining NVIDIA, I did work to deploy containers on the Titan and sort of early Summit systems. So what is NGC, the NVIDIA GPU Cloud? It is effectively a repository for optimized HPC, HPC visualization, and deep learning containers. What differentiates this from something like Docker Hub is that it's curated. So all the containers we post are sort of approved by the development team that's developing the application, and they pass through sort of our QA pipeline. We also try and provide good documentation for our images. This is currently a work in progress, but we'd like users to be able to quickly validate and benchmark the applications we provide. And as of a couple months ago, it's completely free to access. You don't even need to register an NVIDIA account to grab them. Okay, there's a bunch of stuff up here. We're not super interested in all of these. But just to give you some idea on what we'll be talking about today, we're talking about sort of traditional HPC applications and as well HPC visualization. And I've primarily been working with these green containers. These are multi-node containers, and we'll sort of talk about what that means and how we build them. All right, so with NGC, I just want to quickly mention that we have partnered with some universities as well as vendors and OEMs to ensure that NGC as a product integrates well with systems that are deployed. If you have a GPU system and you're not up here, please talk to me at some point today. We'd love to jump on your system and see how we can get NGC containers running there. Okay, so before we jump into sort of multi-node and all the special sauce we try and put into our containers, I want to cover the basics of how GPUs, and in particular NVIDIA GPUs, interact with containers. So CUDA, it's like a very overloaded term. It means lots of things depending on the context it's used within. So I want to dissect it a little bit and go over the anatomy. So at the lowest level, you have, above the hardware, you have some kernel space display driver. It's a pretty standard kernel space display driver. Okay. When these kernel modules are loaded, they create some device files and dev, and figure out how, okay. And the dev device files are used by a set of user space driver components. So for example, libcuda.so, libgl.so, as well as some driver binaries like NVIDIA SMI, if you're familiar with it, sort of form the user space driver component. So in total, when we say the CUDA driver, it's actually two components. There's a kernel module component, a kernel space component, and a user space component. And on top of all that, we have the CUDA toolkit. If you've ever used the NVIDIA GPU system, this is basically everything that by default is installed in user local CUDA. So this includes sort of our compiler toolchain, the NVCC CUDA compiler, the CUDA runtime, which is how most developers interact with the GPU. That's libcuda.rt.so, not to be confused with libcuda.so, as well as a bunch of optimized math libraries and debuggers and things of that nature. So our job today is sort of to figure out where the boundary for our container lives in this chart. So to determine that, we have to know how all of those components interact with each other. We're going to run through this. Looks like the red's hard to read. That's okay. The takeaway is pretty simple on the next slide. So the user space and kernel space driver components are exactly version matched. If you're on a CUDA system with it's appropriately set up, You look at the version of one of the CUDA modules, such as the DRM kernel module, that version will exactly match libcuda.so, for instance. And there is no cross-version compatibility there. Similarly, the toolkit runtime components, like libcuda.rt.so, does not maintain cross-version compatibility. So you can't compile an application in a container with CUDA 9, and then at runtime, like bind, mount, and host, CUDA runtime components for CUDA 10. That will not work. Additionally, there is some coupling or constraints imposed between the toolkit and the driver. So for a given toolkit, there is a minimum driver version required. So for instance, if you compile an application with the CUDA 9 toolkit, the minimum driver is 384. It can run on a host with newer drivers, like 410, but it cannot run on older drivers, such as 346. So if we take all of these constraints, we can sort of develop a strategy for building our container. So at build time, we want to bundle the CUDA toolkit runtime components in the container. We want to bake them in. We can't mix and match runtimes, so we should just put them in the container. A really important note, if you get anything out of this presentation, I hope that it's, I can sort of make clear that to build CUDA applications, to build CUDA containers, the toolkit can be installed and run on any system. I have CUDA toolkit on this laptop, which, don't tell my boss, it does not have an NVIDIA GPU inside of it. This will work with the remote builder, for instance. At Singularity has the toolkit is effectively a compiler that cross-compiles for whatever GPU architecture you want it to. So there's no requirements to build your container. But you should package the runtime components of the toolkit. Now, we don't have any control from our container over the kernel module that's loaded, the kernel space component of the driver. And so we really are almost forced to bind mount in the user space driver components. So bind mount in from the host to the container, things like libcuda.so. We also need to mount the device files as well. But the takeaway is, if you build a container and leave the toolkit components inside of it, and you mount at runtime in some driver components, then the only requirement you need to ensure that a container will run on a given system is the system has to have a minimum driver version installed on it. So here's a big list, not super important, but you can see for any toolkit version, you have to maintain some minimum driver version. I'm going to skip backwards compatibility. I know this is hearsay that I'm mentioning NVIDIA Docker here, but this is a product that NVIDIA provides, an open source product, which handles like bind mounting in the correct user space driver libraries into the container if you're using Docker, and ensures that the host driver version is compatible. That's all I'll say about that, I promise. If you've ever built a container, you know that containers generally are bootstrapped from other containers. And so to facilitate this, NVIDIA provides Ubuntu and CentOS base images. These come with the toolkit components all set up and ready to rock inside of them. Pretty much recommend, if you're making a GPU container targeting almost any container runtime, will save you a lot of headaches to just use one of these base images to start with. And these are available on Docker Hub as well as NGC. I'm going to skip stub libraries. So Singularity has NVIDIA support baked in with the --NV flag. When you use that flag, what it does is consult this nvliblist.conf file, which has a list of user space driver components that need to be visible to the container from the host. NVIDIA also has NVIDIA Container CLI, just sort of a CLI interface to the inner workings of NVIDIA Docker. And if you install this tool on your system, Singularity will automatically use the list of files that the tool provides to figure out what to mount into the container. And the reason you might want to do this is NVIDIA Container CLI is a dynamic application that's a little bit more robust than a static config file. Okay, so that was a real quick overview of how you should really handle GPU containers. Now I'll go into some of the additional things we do to NGC containers to try and differentiate them. So first off, what are we targeting with these containers? So all our NGC containers are targeting x86, sort of our enterprise class GPUs. We assume that if the system has Mellanox InfiniBand, maybe NVIDIA InfiniBand now, I don't know, that the user wants to make use of it. We assume that if there's a Slurm or PBS like resource manager, that we would like to integrate well with it. Docker's probably not available, and a constraint we impose on ourselves is we would like a single image to sort of cover any system that looks like this. Okay, so as I mentioned, Docker's generally not available. That's why we're all here on these sort of HPC resources. But NGC is a Docker registry. Luckily for us, Singularity works really well with external Docker registries. So it's a single command to pull or build from NGC or any other Docker registry for that matter. There are some constraints if you're building images and you're going to target Docker and Singularity or Charlie Cloud or whatever runtime's popular. You may have to consider that the image will not be writable at runtime. This is something that Docker takes for granted. Like people that build Docker images assume that at runtime you can write or have the impression that you're writing to the image, and that's not true with things like Singularity. Docker entry points are pretty popular. If you're not familiar, the entry point is like a script that's run on container startup that's generally used to sort of dynamically set up the runtime environment. And we'll go over how we use that for the NGC containers in a couple slides. But we have to be careful because different runtimes handle this script differently. So Docker, it sort of transparently just works. With Singularity, exec and shell do not run the entry point, but Singularity run does execute the entry point. Okay, so we target Pascal, Volta, and Turing generations of GPUs. We would like to have a single container that can, optimally make use of these GPUs. And so ideally, we would use NVCC's sort of fat binary capability to do this. That sort of just works. It's very simple. But what we find is a lot of scientific applications have a build system on top of them, and that build system doesn't always expose this fat binary creation ability. And so what we need to do there is create Pascal, Volta, and Turing binaries of our application and use the entry point script to query the host when the container starts and set the path and LD library path up appropriately so that the Pascal version of LAMPS is picked on a Pascal system and the Volta version is run on a Volta system. We'll skip that. Multi-node, everyone in HPC likes to talk about multi-node containers. They're very challenging. Not everything is figured out, so I'm sort of presenting the strategy we're currently taking, but this is hopefully a dialogue, so I'd like to hear what other people are thinking. We currently use OpenMPI as the basis of our multi-node support. OpenMPI has sort of a plug-in or component-based architecture with a lot of the decisions on which component should be used saved until runtime. And this makes it really ideal for portable containers. So for instance, we can put OpenMPI inside a container, load it up with lots of components, and then at runtime, based upon the system we're running on, sort of the correct component will be picked. And I'll go over some of those components now. So for InfiniBand support, OpenMPI makes use of UCX, which is a library maintained by Mellanox or NVIDIA primarily right now. Its default in OpenMPI 4 replaces the OpenIB component, which I think is a good thing. Similar to OpenMPI itself, UCX sort of has a component architecture. And so it supports InfiniBand, GDR copy, CUDA IPC, KNEM, XPMEM, CMA, and all these fancy ways of moving data around. And what it will do is query the host system at runtime. Again, this is like very important and useful to us to pick a transport that's not only optimal, but one that's actually supported by the host. So, for instance, GDR copy is a way to optimize GPU memory transfers, but it requires a kernel module be in place. If you're running a container that was built with UCX and GDR copy, it will still work in the absence of GDR copy on the host. UCX will just disable it. So this like dynamic support is awesome. It really helps with portable containers. For InfiniBand support, we provide that through Mellanox's OFED distribution, as well as for the community's supported RDMA core project. We also support extensions such as NVPureMem and GDR copy, which sort of extend IB verbs. Similar to the GPU, there's user and kernel space components to the Mellanox driver. So this is problematic. As we heard yesterday, like at least with versions of MoFed less than 4.4, generally there is no cross-version compatibility. So if the host is running MoFed version 3.4, your container had to have the user space 3.4 components in it or it would just blow up. And this was brought up yesterday. This is something I'd like to work on. But playing the same game we do with the GPU is not as trivial with Mellanox. So for instance, libIB verbs, which is one of the user space libraries that enables InfiniBand support, relies on libNL. libNL is named differently in RHEL and Debian distributions, and so if you go to mount in libIB verbs from a RHEL host to an Ubuntu container, you have to do something to make sure the dependencies are set up. And so potentially you can pull in all of the dependencies into your container, but it feels like a slippery slope at some point. At some point you get down to libc and you don't want to be pulling that into your container. And just to sort of discuss this a little bit more, libcuda.so and all the user space CUDA libraries don't have any external dependencies other than libc. So very simple to pass those in. So we can't assume that all centers are running like up-to-date MoFed driver stacks. So what we currently do is package multiple OFED and RDMA core releases into the container. So we have to relocate a bunch of packages. Then at runtime, we read the kernel module version, correlate that to the sort of release version of the MoFed, and then we patch up LD library path and IBV drivers to point to the correct relocated installation. InfiniBand does not like to be relocated. It's like a big pain. There's a couple extra bullet points maybe below this to get it set up correctly. PMI, we had a great talk yesterday about this. I'd just like to say PMIX is like going in the right direction. It's like helping out, making our containers more portable. It is only as good as sort of the resource manager that enables it though. So lots of resource managers either don't have PMIX support or it's in very new versions. And so our containers, we carry around Slurm PMI2 support in case we run into that situation. Okay, so we've got a couple minutes. So we've run through, we've created this amazing container. How do we actually launch it on a cluster? So there's a couple different ways we'll sort of go over. The canonical way is to assume that MPI in the host is available and compatible with MPI in the container. And you can tell your users, okay, instead of running MPI run command, sandwich singularity run into your image in there. That's got a very familiar interface. You maintain sort of integration with the resource manager. The con is that you're mixing components of MPI outside the container and inside the container. And so that's where you run into ABI compatibility issues, PMI issues, and it can be pretty complicated. So OpenMPI 4 and PMIX, it's like a step in the right direction. Cross-version compatibility is actually pretty good. I think OpenMPI 5 will be ABI compatible with 4, hopefully. But there's some devil in the details using this method. If you're running Slurm, your users might want to use srun. This is very similar to using an external MPI run. The only thing you have to really keep in mind is that srun can handle multiple PMI versions. Those versions are often optional. So the system administrator may have installed sort of the PMIX components for Slurm, or it may not have. But the user has to know what components are available and specify that in their srun command. There's another way. If you're not on a system with a compatible OpenMPI install or a compatible Slurm install, you can run MPI run inside the container. There's a couple ways to approach this. I prefer this method, although I'm always interested to hear what other people think. So the basic strategy, we'll go through this. Let's see if this thing, I believe it does not. Okay, this thing's dead. Okay, so the top block that begins with host file, that's our resource manager integration. That's as far as it gets. The resource manager will provide us a list of nodes, and if we need to put that into a host file that OpenMPI can consume, so it knows where our job will be running. The second block of text, all these OMP, MCA, PLM environment variables, those can also be set as MPI run flags, but the first two, MCA, PLM, and PLM RSH args, those instruct OpenMPI to sort of bootstrap itself with SSH. So it'll SSH into each node, sort of start the process off. The last line is very important. The last line of the second block, the ORT launch agent. What this does, you can see we have singularity run, our image, and a command called ORTD. ORTD is the OpenMPI process manager. So what we're telling MPI run to do is to start the process manager inside of a container. And so we get to the very last line. So we can call MPI run inside of our container, singularity run, MPI run, give it the list of nodes we want to run on, and finally our command. What will happen, MPI run inside the container will SSH to each node that's we've told it about in the host file and start the ORTD process manager up on each node inside a container. Presumably ORTD will like fork off our actual command we want it to run, but that's done inside the container. So everything's containerized here besides SSH. So the benefit is it works on most systems as long as you can SSH to nodes that you've allocated with your resource manager. Your workload's better contained, so hopefully better reproducibility since you're not relying on many external components. But you pretty much lose all integration with the resource manager, so you're sort of bypassing the resource manager and starting up your own daemons inside containers. And there were some ellipses on the last side for that PLM RSH args. These are SSH arguments to make sure that you can SSH into each node correctly, and those vary from system to system. I would not expect your average user to know what those arguments should be. Okay, right on time with about 30 seconds left. Image size. I'm going to be very serious here. I'm not mad at the HPC community, but I will say I'm disappointed. You all make images that are way too big, way too big. I've seen 50 gigabyte TensorFlow container, and that should not be happening. Something's gone wrong. Docker has the idea of a multi-stage build, which we won't go into it. Singularity's working on a similar concept, but this allows you to separate your build environment, which is filled with giant compilers and things like that, from your runtime environment, which should be very lean and small. You can also use tools like Dive, which helps you sort of audit an image and see, correlate the command you ran in your recipe to how many files it generated and how large they are. And just to sort of give you an idea of what you can do if you put a little bit of time into this, our LAMPS container is about 100 megabytes compressed on disk. It contains multiple LAMPS binaries. It contains a slew of OFEDs, Slurm support, all kinds of stuff. A single LAMPS binary, like uncompressed, is 70 megabytes. Like, just because you jam everything inside a container you can think of does not mean it has to be large. We could shave off some more megabytes there. That's what I sick my interns on usually, is make this container smaller. There's cruft in here. Community support, I'll just mention this super quick. I know we're about out of time. So we're not just making containers and throwing them out there. We do want to engage the community and be part of the community. I mentioned our NVIDIA Docker project. We also have a tool called HPCM, HPC Container Maker. And this provides like a Python abstraction above sort of your Docker file or your Singularity recipe. So you can write in Python and then generate a Docker file or an HPCM recipe. And I should just mention, we use this like internally for like everything we post on NGC, as well as internal benchmarking and things like that. It's pretty handy. We also have, we participate in, sort of kicked off the HPC Advisory Council. This is a council of like-minded folks such as yourself. Anyone is welcome to join. We basically have once or twice a month a con call to describe what issues we've run into and try and find actual tractable paths forward. So if anyone's interested in sort of joining this, no big commitment required. You can join if you have time, and we'll just send you invites as we set up meetings. Just come talk with me. And that was, I think my time's up now. So are there any questions over anything I covered? Okay.
Let me get the mic over.
Oh.
Hey, Adam, great talk. Thanks very much.
You.
Yeah, so I do have a couple of questions. Let's see. First off, okay, so right now, yeah, as you mentioned earlier, we support well, Singularity supports the --NV option. As you may or may not know, I mean, you probably do. It's kind of kludgy the way we do it, and it might. One thing that I worry about is how sustainable it's going to be if NVIDIA starts deciding to like change what user libraries are installed with the driver or stuff like that. So you might have heard yesterday, we're hard at work on creating a plugin system.
Yes.
Would NVIDIA be interested in maintaining the --NV option moving forward?
So I am not in a position to say NVIDIA will or will not maintain that. I'm definitely interested in looking into that to see if that's something we can do. Like I said, I think we're actually most of the way there with that NVIDIA Container CLI utility.
Right.
Like I said, it's sort of a portable way to query a system and determine what libraries need to be put in the container. So hopefully we can have a thin wrapper over that with the plugin interface.
Right, right. So who should I talk to? Felix or somebody else?
Can you just send me an email and I will either address it myself or find the right person.
Okay, cool, cool. Right. Sounds good. Yeah, so everybody should work together. And one more question. Okay, that was a really, really interesting way to spawn MPI from within the container. So it's nice because you don't actually go in and hack the SSH inside the container, which is, I know, what I've done and some other folks have done as well. And that question comes up a lot. So do you have that documented anywhere? If not, could we try to document it somewhere? Because I know it's not, I know it depends a little bit on your environment, and that's, one of the troubles, but.
Yeah, it is documented in this slide deck. I assume you'll get a copy of that. I'm definitely willing to share everything I know about that. No, that's no problem. But we do not have a page up that describes in detail that process.
Okay, cool. Yeah, maybe we could work together with you to get that up on the Singularity document.
Yeah, absolutely.
Awesome.
Absolutely.
Thanks, Adam.
So I was a bit nervous yesterday when I presented the slides, not to talk about the second mode, which you just mentioned. Yes, some of our users who use Kubernetes with Mellanox software and MPI, the new so-called new generation users, they actually prefer the second mode because that works in various ways with network namespaces, without network namespaces, with Kubernetes, and without.
Just to be clear, you mean passing in the user space driver libraries?
No, I mean the MPI run inside.
Oh, okay. Yes.
MPI run inside the container which spawns off the other one. So,
okay. Yeah, the one difference I would say that probably comes up there is in Kubernetes, and this is not something I'm super familiar with, but generally you don't even have an SSH daemon that you have access to. And what I like about this approach is there is the SSH requirement, but then you don't have to play around with keys. Exactly. If users are generating keys, they're going to leak their keys out.
Yeah, and the reproducibility part, everything is pretty much contained inside your container. You don't have to do host bind mounts from the outside, and that's more predictable way to do things. So there are both sides to it. And yeah.
You got one.
So, simple question, hopefully. What about MPitch?
Well, you can use that second MPI option and use OpenMPI. In all seriousness, I like MPitch. It's obviously used by lots of vendors such as Cray. I used it for the Titan system. It has pretty good ABI compatibility between the flavors, which is great. What it is lacking, and this is a work in progress, is it doesn't fully support GPU-aware MPI through the UCX layer. There's a component that's required in MPitch itself, and it doesn't support sort of the plug-in nature of OpenMPI. So for instance, as far as I'm aware anyways, if you're running MPitch and you want to run on Slurm's PMI2, you need a MPitch Slurm PMI2 installation. Whereas if you want to run under PMX, you need a PMX MPitch installation. So it's, I like MPitch. It's a lot simpler in some ways to OpenMPI, but you lose the flexibility. So
I think one last question on the other end.
We're definitely open to hearing about these things, though. Like if you have to have an MPitch container or you have a good reason we should, like that's something we would absolutely take into consideration.
So yeah, basically I don't want to make that decision for my users. I want the developers to say, I want MPitch or I want OpenMPI. That's sort of the power of containers in its own right. So I don't really care that much about MPitch other than we should have more options.
I fully agree.
Hi, Adam. My name is Nigel. I'm a researcher here on Comet. I'm interested in the work that you're doing for benchmarking because one of the projects that I'm working on is very closely aligned with that. So my question, first a comment. With the benchmarking, is it possible, because there's a lot of graphs online, but they often don't have like quants or versions or anything like that, so that would be helpful to know. And then my question would be, do you have any recommendations for running Kepler architecture? Because here we have Kepler, Pascal, and Volta, and I'm using some NGC containers, so I wonder if you have any suggestions for.
Yes, so I'll just let you down right off the bat. I don't have good answers to either of those questions. So as far as benchmarking numbers, that would, I guess, depend on exactly what type of document you're referring to. Internally, we keep track of exactly how we ran all the benchmarks, what systems, like full tracing of the system, why it's in progress. But generally, when Jensen's giving his keynote, that cruft doesn't make it on there. You get a nice green bar chart where NVIDIA GPUs are a lot faster. If you have any particular questions, like if you have a graph and you want to know where the numbers came from, this could get out of hand, but if you email me, I can at least try and figure out more details about the exact system configuration and actual like quantitative data associated with it. But yes, and I will say though, all those pretty bar charts, like that information absolutely exists and comes out of PerfLab. As to your second question, unfortunately, we've sort of drawn the line at Pascal for NGC support. NGC is a relatively new product. I think it's about 1.5 years old, maybe 2 years. And so that sort of was birthed during Pascal. And so we don't retroactively add Kepler support. So I don't have anything good to tell you there, other than you can use our tools such as HPCM, for instance, to sort of build your own containers. And I should mention this is something that's sort of slow off the line, but we've started adding in the HPCM recipe as well as the Docker file into the images themselves. So in theory, you can download a container once we've fully implemented this, pull out the Docker file, modify it for Kepler, and use it.